Welcome! In this session, we'll explore problem number 1079, titled Letter Tile Possibilities. We'll break down the problem step by step and discuss different approaches to solve it. Let's dive in and learn together. Imagine you have a set of tiles, and each tile has a letter printed on it. Your task is to figure out how many unique sequences you can create using these tiles. Each tile can be used as many times as it appears, and you can arrange the tiles in any order. For example, if you're given a string of tiles, the goal is to determine the total number of distinct, non-empty sequences that can be formed. The input will be a string consisting of uppercase English letters, ranging from A to Z. The output is an integer that represents the total number of these unique sequences. Let's break this down with an example. Suppose the input string of tiles is AAB. From these tiles, you can form several unique sequences. For single-letter sequences, you have A and B. For two-letter sequences, you can form AA, AB, and BA. And for three-letter sequences, you can create AAB, ABA, and BAA. Altogether, there are 8 unique sequences you can generate from the tiles AAB. Now, if the input is a bit more complex, like AAABBC, the total number of unique sequences jumps to 188. This includes sequences with repeated letters and different orderings of the tiles. Now consider a simpler example where the input is just V. In this case, there's only one tile, so the only sequence you can form is V. The output here would be 1. To add more detail, let's look at the constraints. The length of the tile string will be between 1 and 7, and the tiles themselves will always be uppercase English letters. For edge cases, if the tiles contain only one type of letter, such as A, the output will be 1, because you can only form one sequence. On the other hand, if all the tiles are unique, like ABC, the total number of unique sequences is the sum of all permutations of lengths from 1 to the length of the string. For instance, with 3 unique tiles, you would calculate 3. For 3-letter sequences, plus additional sequences of shorter lengths, resulting in 15 unique sequences. Finally, if all the tiles are identical, such as quad A, the number of unique sequences corresponds to the lengths you can form, AA, AAA, and quad A, giving a total of 4 unique sequences. To start with, we considered the brute force approach, which involves generating all possible permutations of the tiles. The intuition is straightforward. For every tile, you pick it as the starting point, recursively generate permutations of the remaining tiles, and add each sequence to a set to ensure uniqueness. While this method ensures that we account for all possible combinations, it is computationally expensive. The time complexity grows factorially, at O(n), for a string of length n, and the space complexity is also O(n), because we need to store the results in a set. The main drawback is inefficiency, as this approach generates a lot of duplicate sequences, especially when the input contains repeated letters like AAB. Although the set helps remove duplicates, it introduces additional memory overhead, making this approach impractical for larger inputs. A more efficient strategy is to use backtracking with frequency counting. Instead of generating all permutations and removing duplicates afterward, we prevent duplicates from being generated in the first place. The key insight here is that each tile can only be used as many times as it appears in the input. By keeping a frequency counter, such as a dictionary, we can track how many times each letter is available. As we recursively build sequences, we decrement the frequency of the chosen tile and restore it during backtracking. This systematic exploration ensures that we only generate unique sequences. The time complexity of this approach is O(k*n), where k is the number of unique letters and n is the length of the input. This is a significant improvement over brute force because it avoids redundant work. Additionally, it requires only O(k) space for the frequency counter and recursion stack, making it much more memory efficient. Another possible strategy is iterative subset generation. Here, the idea is to generate all subsets of the tiles, including duplicates, and then calculate the number of permutations for each subset. This approach avoids recursion by using a mathematical formula based on factorials to compute the permutations. However, its complexity lies in the subset generation, which has a time complexity of O(2 to the power of n), and in calculating permutations for each subset, which adds an O(n) factor. The space complexity is also higher, at O(2 to the power of n), because we need to store all generated subsets. While this method can be mathematically elegant, it is less practical for larger inputs, as it becomes harder to implement efficiently without running into performance bottlenecks. The chosen strategy is backtracking with frequency counting, as it offers the best balance between efficiency and simplicity. By design, this approach avoids generating duplicate sequences, which eliminates the need for a set and reduces memory usage. It is intuitive to implement using recursion and significantly more efficient than brute force. The main trade-off is that it requires careful management of recursion to handle large inputs without running into stack overflow issues. The key breakthrough here is realizing that tracking the frequency of tiles allows us to eliminate duplicates during sequence generation itself. This makes the backtracking approach not only optimal in terms of time and space complexity but also elegant in its execution. Ultimately, it provides a robust solution to the problem without the inefficiencies of alternative methods. To solve the problem of generating all unique permutations of a given set of letter tiles, we start by clearly defining our task. The goal is to consider all possible arrangements of the tiles, ensuring that no duplicates exist in the final output. For example, if the input is AAB, our result must include AAB, ABA, and BAA, but should not repeat any of these. Now, since the input may contain duplicate characters, it's critical to ensure that our algorithm handles this efficiently by avoiding redundant work. The good news is that the input size is relatively small, up to 7 tiles, making recursive techniques like backtracking a feasible choice. Our approach will use backtracking to explore every possible arrangement while leveraging a frequency counter to track how many tiles remain available. This ensures duplicates are avoided at their source. We'll initialize our algorithm by creating a dictionary that counts the frequency of each tile, which allows us to dynamically manage which tiles can still be used as we build permutations step by step. In addition to the frequency counter, we'll use a list to construct permutations dynamically as we progress through the algorithm. Optionally, to ensure uniqueness, we can use a set to store the results, though this can often be avoided by ensuring uniqueness during the construction phase itself. Next, we define the recursive backtracking function. The base case for this function is simple. If the length of the current permutation matches the total number of tiles, we convert the list into a string and store it in our result. For the recursive case, we iterate through the frequency counter and, for each tile with a positive count, we append it to the current permutation and decrement its count. After making a recursive call to explore further, we backtrack by removing the last tile and restoring its count. This process continues until all possible unique permutations have been generated. Finally, once all recursive calls are completed, we return the list of unique permutations as the result. Backtracking is particularly well suited for this problem because it allows us to build solutions incrementally. Whenever a choice leads to an invalid state, such as a duplicate permutation, we can undo it and try a different approach. In this context, invalid states are avoided by carefully managing the frequency counter, which ensures that duplicate tiles are not overused. The frequency counter is key to maintaining efficiency because it removes the need for post-processing to eliminate duplicates. Instead, we prevent them during the recursive process itself. By skipping tiles with a count of 0, we prune the recursion tree and avoid unnecessary computations. This optimization ensures that the algorithm remains efficient even as it explores all valid permutations. To summarize, the frequency counter helps us track available tiles, and the dynamic list structure allows us to efficiently build and backtrack permutations. Both data structures are critical for ensuring correctness and efficiency. An optional enhancement to the solution is using a set to store the results. This guarantees that the output contains only unique permutations, though in many cases, the algorithm's careful construction process eliminates the need for this extra step. Regarding complexity, the time complexity of generating all unique permutations is O(n), where n is the number of tiles. This factorial growth reflects the number of possible arrangements. However, the actual runtime is often faster due to the reduced branching factor when duplicates are present. The space complexity is O(n) for the recursion stack, as we build the permutations recursively, and O(n) for storing the results, given that each unique arrangement is stored in memory. The provided Python implementation demonstrates this process step by step. It begins by initializing the frequency counter and result set, defines the recursive backtracking function, and finally returns the list of unique permutations. In the implementation, the recursive backtracking function handles the core logic. For each tile with a positive count, we append it to the current permutation, decrement its count, and make a recursive call to explore further permutations. Once the recursive call completes, we backtrack by removing the last tile and restoring its count in the frequency counter. This ensures that all choices are correctly undone before exploring other possibilities. The algorithm begins by constructing the frequency counter using Python's counter from the collections module. The result is stored in a set to ensure uniqueness, and the backtracking process starts with an empty list. After all recursive calls are completed, the result set is converted to a list and returned. For example, calling generate_permutations, AAB, produces the output, AAB, ABA, BAA, demonstrating the algorithm's ability to handle duplicates efficiently while generating all unique permutations. This solution for LeetCode problem number 1079, letter tile possibilities, is implemented using a backtracking approach. The goal is to calculate all unique sequences that can be formed by rearranging the given tiles, accounting for duplicate characters. Explanation of the code. 1. Imports and initialization. The counter class from collections is imported to efficiently count the frequency of each character in the input string. The number tile possibilities function is defined as the main entry point, which takes the input string tiles. 2. Backtracking function. The backtrack function is defined as a nested helper function. It takes the counter of character frequencies and calculates the total number of possible sequences. The total variable is initialized to 0. It will store the cumulative count of sequences for the current state. 3. Recursive exploration. The loop iterates over each character in the counter. If the character's count is greater than 0, it means this character can still be used to form sequences. For each usable character, the count of the character is decreased by 1, indicating its usage. The total is incremented by 1 for the current sequence, and the result of recursively calling backtrack with the updated counter. After the recursive call, the count of the character is restored, backtracking, to ensure other recursive paths remain unaffected. 4. Base case and return. The recursion automatically stops when all characters in the counter have a count of 0, no more characters to use. The total count of sequences for the current state is returned. 5. Initial setup and execution. A counter object, char_count, is created to store the frequency of each character in tiles. The backtrack function is called with char_count, and the result is returned as the final answer. Key insights. Efficiency. By using a counter, we avoid generating duplicate sequences, making the solution efficient for small input sizes like this problem. Backtracking. This approach ensures that all unique sequences are explored without explicitly generating each one, thereby reducing memory usage. The solution is optimal within the constraints, as it works recursively through all possible combinations while ensuring no duplicates are counted. This implementation is concise yet powerful, leveraging backtracking to handle the complexity of duplicate characters effectively. Here, we begin by importing the necessary libraries and defining our class, solution. The main method, numberTile possibilities, takes in a string called tiles. To solve this problem, the first step is to count the frequency of each character in the input string. We use a hash map for this purpose. The for loop iterates over each character in the string, and for each character, we update its count in the map using the getOrDefault method. This ensures that if the character is not already in the map, it starts with a count of 0, and then we increment it by 1. After building this frequency map, we initiate the backtracking process by calling the helper method backtrack, passing in the charCount map. This is where we'll explore all possible combinations of tiles recursively. In the backtrack method, the variable total is initialized to 0 to keep track of the number of possible sequences. We then iterate over all the keys in the charCount map, which represent the unique characters. If the count for a character is greater than 0, it means this character can still be used. We decrement its count in the map to simulate using this character. Next, we add 1 to the total to account for the current character being used, and then we recursively call backtrack to explore further combinations with the updated character counts. After this recursive call, we backtrack by restoring the characters count in the map to ensure we don't affect other recursive calls. Finally, once all possibilities have been explored, the method returns the total count of sequences that can be formed. To solve this problem, we begin with the input string AAB. The first step is to count the frequency of each character. Here, we see that there are 2 occurrences of A and 1 occurrence of B. This gives us the dictionary, A2, B1. Next, we use recursive backtracking to explore all possible combinations of tiles. The backtracking function initializes with the character count dictionary, and our goal is to systematically reduce the counts as we select characters. For the first recursive call, we start with the full character count and a total of 0. We choose A, which reduces its count to A1, B1. This reduced dictionary is then passed into the next recursive call. Now, in the second recursive call, we again choose A. This reduces its count further to A0, B1, and we recursively call the backtracking function once more to continue exploring paths. Continuing the process, in the third recursive call, the character count is now A0, B1. At this point, we choose B, reducing its count to A0, B0. With no characters left to choose, we hit the base case and return 0. After this, we backtrack by restoring the count of B2, A0, B1. At this stage, we add 1 for the choice of B, making the total 1. We then backtrack further by restoring it to A1, B1. Adding 1 for the previous choice of A, the total becomes 2. The exploration continues with B as the first choice. After exploring all paths and combinations, we find that the total number of unique combinations for AAB is 8. This total includes all possible sequences of tiles, accounting for both single-character and multi-character combinations. Now, let's examine a new example where the input is ABC. We start by counting the frequencies of each character, which gives us A1, B1, C1. Since each character appears only once, this is a simpler case. Using recursive backtracking, we begin by choosing any of the characters A, B, or C and then recursively explore the remaining paths. For instance, if we start with A, we reduce its count to A0, B1, C1, and proceed recursively. From there, we can choose B, reducing the count to A0, B0, C1, and then choose C. After each complete sequence, we backtrack to restore the counts and explore other choices, such as starting with B or C instead. By systematically exploring all paths and restoring counts during backtracking, we ensure that every possible combination is considered. At the end of this process, we find that the total number of unique combinations for ABC is 15. Finally, let's consider the input AA. Here, the character count is 2. We start the backtracking process by choosing A, reducing its count to 1. From there, we choose it again, reducing the count further to 0. At this point, we reach the base case, where no characters are left, and we backtrack to restore counts. The backtracking process ensures that all paths are explored, including both single-character and multi-character combinations. For AA, the total combinations are 3, AA, and A, from separate paths. This example highlights some key observations about the process. Backtracking is essential for exploring every path while restoring character counts. The use of a counter allows us to efficiently track the availability of characters. Finally, the total output is simply the sum of all valid paths, ensuring that no combination is missed. The time complexity of our solution comes from the backtracking process, which systematically explores all possible sequences of letters that can be formed using the given tiles. At each step, the function iterates over all distinct characters in the counter. For each character that still has a non-zero count, it decrements the count, makes a recursive call, and then restores the count as part of the backtracking process. To understand the total number of recursive states, consider the ways we can arrange the input tiles, including all possible subsets. For a string of length n with distinct characters, there are up to n permutations. However, if the string contains duplicate characters, the number of permutations is reduced because repeated characters lead to redundant arrangements. This reduction is mathematically expressed as n. divided by the product of the factorials of the frequencies of each distinct character, represented as frequency underscore 1, frequency underscore 2, and so on, for all k distinct characters. This formula accounts for the total number of unique permutations of the tiles. Now, consider the number of recursive calls. The backtracking algorithm explores all subsets of the tiles. For a given set of n tiles, there are up to 2 to the power of n possible subsets, since each tile can either be included or excluded in a subset. In the worst-case scenario, where all characters are distinct, the number of recursive calls is proportional to the sum of the lengths of all subsets of size 1 to n. This sum is approximately n*2 to the power of n. Therefore, the overall time complexity of the backtracking approach is n*2 to the power of n, where n is the length of the input string. This accounts for both the recursive exploration of subsets and the generation of permutations within those subsets. Now let's consider space complexity. The depth of the recursive call stack is proportional to the number of tiles being processed, which is n, where n is the length of the input string. Additionally, the solution uses a counter object to store the frequency of each distinct character in the input string. This object requires space proportional to the number of unique characters, which is k, where k represents the count of distinct characters. Beyond these, no additional data structures are used apart from the recursive call stack and the counter. Therefore, the total space complexity is n plus k, combining the stack depth and the space needed for the counter. When comparing the backtracking approach to a brute force method, the advantages become clear. A brute force approach would generate all possible permutations of the tiles, including duplicates, and then filter out the duplicates afterward. This process requires generating n permutations, which is computationally expensive and inefficient. In contrast, backtracking directly avoids duplicates during the generation process by skipping over characters with a zero count. This makes the backtracking approach significantly more efficient since it doesn't waste time creating and filtering redundant permutations. By directly generating unique sequences, the algorithm avoids unnecessary work and reduces the overall computational overhead. We can analyze the algorithm further by considering the best, average, and worst-case scenarios. In the best case, where all characters in the input are identical, there is only one unique permutation. This reduces the time complexity to n, as the backtracking process terminates quickly. In the average case, where the input contains some duplicate characters, the complexity lies between n and n*2 to the power of n, depending on the number of duplicates and how they affect the number of unique permutations. In the worst case, where all characters are distinct, the complexity reaches n*2 to the power of n, as the algorithm must explore all subsets and permutations. Mathematically, this complexity arises from the fact that the backtracking process examines all 2 to the power of n subsets, and for each subset, it generates permutations up to size n. The space complexity is similarly justified by the recursive call stack depth of n, and the counter object storage of k, where k is the number of distinct characters. Together, these analyses provide a complete understanding of the algorithm's efficiency. Now, let's look at some common mistakes that can trip you up when solving the letter tile possibilities problem. First, ignoring duplicates in the input can lead to errors or inefficiency. For example, if the input contains repeated characters, failing to eliminate redundant permutations will create duplicate results. A good way to fix this is by using a set to store unique results or by sorting the input and skipping over duplicate elements during recursion. Next, not managing base cases properly in recursion is another frequent issue. Without clearly defined stopping conditions, your recursion could end up causing infinite loops or even a stack overflow error. The solution here is to explicitly define base cases, like when the recursion reaches the end of the input. Another mistake is using inefficient data structures for backtracking. For instance, relying on lists for frequent insertions and deletions can be slow and increase overhead. Instead, a more efficient approach would be to use a Boolean array to track which elements are being used. Lastly, overlooking edge cases, such as empty inputs, single-character inputs, or inputs where all characters are the same, can lead to incorrect results or runtime errors. Testing your solution with diverse input cases, including these edge scenarios, is key to ensuring correctness. Over-optimizing too early is another common pitfall. Jumping straight into complex optimizations without first implementing a working brute force solution can make debugging harder and waste time. The better strategy is to start with a simple, correct solution and then optimize it step by step, as needed. Now, when preparing for interviews, it's important to recognize key patterns. Many problems involving permutations or combinations rely on backtracking, so identifying this early can help you structure your approach efficiently. Interviewers often ask about optimization as well, such as how to handle duplicates or improve time complexity. Be prepared to discuss trade-offs, like using extra space with a set for efficiency. Another tip is to clarify the problem scope up front. Ask whether the input has constraints like duplicates, a maximum size, or specific ordering rules. This can help you understand if edge cases need special handling or if your solution requires further optimization. Additionally, writing reusable code is a valuable habit. Breaking your solution into clean helper functions doesn't just improve readability, it also makes adapting your logic to variations of the problem much easier. Finally, exploring related problems can deepen your understanding of the core concepts. For example, LeetCode 46 focuses on generating permutations, while LeetCode 47 tackles permutations with duplicate elements. LeetCode 39 deals with combination sums, and LeetCode 78 explores subsets. These problems share techniques like backtracking and recursion, so practicing them can strengthen your problem-solving skills. Now, let's consider alternative approaches. An iterative approach, for instance, uses a queue or stack to generate permutations without recursion. While it avoids stack overflow issues, it can be less intuitive to implement. Another option is dynamic programming, where smaller subproblems are solved and combined into the full solution. This method works well for problems with overlapping subproblems, but it's usually harder to apply to permutation-based challenges. Lastly, bitmasking can be a clever way to generate all possible subsets or combinations by treating each bit of an integer as a flag to include or exclude an element. While this technique is efficient for subset problems, it doesn't generalize as easily to permutations. Each of these approaches has its trade-offs, so understanding their strengths and limitations can help you choose the right tool for the problem at hand. Great job! Today, we tackled the letter tile possibilities problem and learned about recursion, backtracking, and optimizing brute force solutions. Keep practicing these concepts, and you'll master combinatorial problems in no time. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!